This is the simplest possible way to show the asymptotic distribution for the OLS estimator. So this is the method of moments case. We have identification result like this, and just we replace the expectation with sample average. That's just what we do here in this estimator. And we will analyze one by one. This analysis is possible because there is closed form solution for the estimator, right? So this is simplest, right? First, this converges in probability to xi transpose by the weak lobe large numbers, right? And then uh, say this is k by k matrix, and this is also k by k matrix, right? So remember, if you think about a function h, say h of a equals a inverse. This is a inverse function, right? If you enter k by k matrix, then it returns a k by k matrix that is inverse of the matrix. H is continuous if a, like say, if determinant of a is not 0, right? So the function is not determined, not defined when the determinant is 0 because it's not invariable. Everywhere else, it is well defined. It is exactly same as like this. This is continuous except for x equals to 0. Okay, so we know this is continuous. So then by the continuous mapping theorem, um, we have so this convergence is converted into convergence of the inverse. This is because the matrix is assumed to be invariable. Okay, that was the first part. We have done part A. Part B. Now we analyze this one, and we are going to consider the central limit theorem form first, right? Then we have this by the central limit theorem. Okay, and using like we will first show that this is 0. So it's just by assumption. So this is 0. That is, you don't need to worry about this. And then variance of x times u is right, expectation of ui squared xi transpose minus expectation ui xi times expectation ui x transpose, but these are 0, so we only have this term, and that is that. Or ui squared xi transpose. If you have homoscedasticity assumption such that expectation of ui squared given x is sigma squared, then this guy becomes sigma squared times x inverse, but without that information we get just here. Okay, that's the second part, right? Excuse me. Second part, we just finished the second part. Okay, the third part. Um, so we would like to study this, right? Let me start from beta hat. That is 1 over n x prime inverse and y. Okay, and replace y with the original the regression equation xi times xi transpose beta 0 plus ui. Okay, and then you can see like common pattern beta 0 comes out because this will be cancelled out by this inverse, and then plus this times xi ui. Okay, so we have beta hat minus beta 0 equals 1 over n inverse times, and we get this. And you know we need square root n, so multiply square root n here, and just keep going. And we are going to multiply square root n here for the second term. Okay, so then the idea is simple. We know this converges to this, and we know this converges to normal distribution, right? Say omega, right? So let me give you a little more detail than I did in class. Sorry, here inverse. So we know, we prove that this inverse converges to xi transpose inverse, right? Then this means I will define, say, error term, say error will be defined as the difference, right? Then we know it goes to 0. That is, they are equivalent. These two statements are equivalent. Then what we can write here is this equation becomes star becomes expectation xi transpose inverse plus error term, right? And square root 10 times right, like this. I don't know what happens here. I don't know. So we are going to ignore this guy error term, but to do that, mathematically, what's hidden is we have to show that it, when it is multiplied by this, we have to show this goes to 0. Okay, that is true. This is true because this much does not diverge. We know it goes to 0, and we know it is going to normal distribution. All right, so if it was diverged, for example, we know 1 over n converges to 0, but when you multiply 1 over n to, say, n squared, it is going to infinity. It does not go to 0. So we have to make sure what you are multiplying. So for like if you multiply 1 over n to, say, xn, and then it goes to 0 if xn does not diverge, right? Or of course plus minus, right? So this is what we want, and we know that here. All right, so that means plus something another error term, the error term that goes to 0, so we will ignore that. And now here square root n, sorry. So and then this also follows the central limit theorem, square root n times, we can rewrite this way, and minus expectation of the whole guy, this goes to normal distribution something, right? But so this much is the influence function. This is the influence function, and we know the influence function expectation is 0 because this much is 0, right? But right, this is non-random. Okay, and then v is, now what we just need to do here is v is variance of xi transpose inverse times xi ui. That is expectation of inverse ui squared xi transpose. So here originally I have to inverse, like say the variance of function is x. We are using this form and we know these are 0, and transposed here, u is scalar, so it's multiplied. So this last term's transposition is not taken because it's symmetric. Okay, and then as you know, this equals to expectation xi transpose inverse expectation ui squared xi transpose and xi transpose inverse. The sandwich formula is the final result. And if you assume homoscedasticity, then it will simplify to this form, the common, the undergraduate level OLS variance. Okay, here, this is theoretical part. Then how to calculate? Okay, let's think about this. And the problem in calculating here is all the x are observed. X has no problem. X is observed, but what's not observed is u and the expectation. Expectation is population mean, right? So we are going to replace expectation with the sample mean, and u will be replaced by yi minus xi beta hat, right? So transpose. If we knew true beta, then we could use true beta, but of course it's not available. So then computation is like this. First, estimate beta hat n, and then we calculate u hat this way, and then compute the sample mean of xx prime inverse, and then sample mean of u hat squared times xx prime and times, right? So this is basically another method of moments. Remember, at the beginning of this estimator, our idea is replacing the expectations with sample mean, right? And when you calculate the variance, we are going to do the same logic. And here, of course, this is the variance estimator, variance of, estimator for V, and then standard error for beta hat is square root of V divided by square root of N, all right? So this is approximate standard error.